Okay, thanks very much, Richard. So good afternoon, everybody, and thank you for taking time out of your day to listen into this webinar on cellular IoT technologies. It's been split into two parts. The first, a brief overview of cellular IoT technology, in particular narrowband IoT and category M1 devices. The main focus will be on Cat M1 and NB-1 devices, which are currently the main devices in use in the marketplace today. We'll take a look at some of their uses, and lastly, some of the challenges we face when testing devices. In the second part, my colleague Ryan will talk about integrating modules for the EU and US markets and how you might go about integrating a cellular IoT module. So cellular IoT is not really new technology. It's been around for a little while, but has now started to gain some traction due to networks now supporting and implementing it, and the cost of modules is slowly reducing. It's important to note that there are many other IoT technologies in use today, and some of the more familiar ones are listed on the slide, such as LoRa, Sigfox, Bluetooth, wireless LAN, and many others. Pretty much anything that has a gateway to the internet is being dubbed as an IoT device. It's been estimated that by 2020, which is now, there would be approximately 50 billion IoT devices deployed and in use. And this will grow as more and more devices include wireless modules in the design and deployment. So as an example, the next fridge that you purchase is sure to have options for wireless connectivity, and certainly in the future, there's unlikely to be an option to purchase one without wireless connectivity. So if you need to know whether you've got any cheese in the fridge whilst you're at the grocery store, your fridge will be able to show you that there isn't any cheese, but there's plenty of leftover curry. So essentially, 3GPP have defined three types of IoT category, NB-IOT, EMTC, and EC GSM IoT, and their descriptions are there on the slide. The main focus today, as I've already mentioned, will be on sort of NB1 and Cat M1 release 13 devices, although we will touch on some of the future release features to show how the technology is evolving. Extended coverage GSM IoT won't be covered any further in this presentation due to it not being widely adopted. NB-IOT and Cat M1 are by far the most deployed cellular IoT technologies at the moment. In the US, Cat M devices have seen most deployment, whereas in Europe, NB-IOT has been more widely adopted. But in some cases, network operators have deployed both or are intending to deploy both in the future. So this should definitely be a consideration if you're looking to use either of these technologies in multiple regions. And if you want any further information on network deployments, there's a lot of good information available on the GSMA website and is free to download. So one thing to note is that NB-IOT is often referred to as NB1. NB2 is an enhanced version of NB1, adding several new features from release 14 onwards, and we'll look at some of these later in the presentation. So why would you choose either an NB-IOT or Cat M1 or indeed both devices? Well, many countries are switching off their GSM networks. Some countries are now requiring devices to have fallback technology which isn't GSM as part of a plan to switch off their networks in the future. As an example, US network operators have plans to switch off GSM in December 2020. And we've also seen that some network operators are also switching off their 3G networks, either at the same time as GSM or shortly afterwards. Cellular IoT can provide a better alternative in many applications when compared to GSM, especially in cases where a long battery life is important or difficult coverage conditions are a feature, or low cost is necessary. So having a good link budget makes the technology well suited to challenging environments for low data rate, infrequent transmission requirements. And there are various module solutions in the marketplace which have a very small form factor, making them ideal to integrate into all manner of products. The intention of these modular devices was to always hit a low cost point of a few dollars per unit. Considering the estimated 50 billion and growing numbers quoted earlier, this is a very important factor into the implementation of this technology. So depending on the application, NB-IOT or Cat M1 are seen as viable alternatives to GSM, with the biggest benefits being battery life, coverage, and cost. So in this slide, we've got a comparison of link budgets for GSM, NB-IOT, and Cat M1. So what exactly is a link budget? Well, the link budget defines the signal loss that the system can tolerate and still provide a suitable use case. So an acceptable use case will depend on the application. So where a high reliability is required, the signal-to-noise ratio will need to be high, whereas if lower reliability of the link is acceptable, then a higher link budget can be achieved. The link budget is impacted by factors including transmit power, antenna gain, receiver sensitivity, frequency, path loss, modulation scheme, and signal-to-noise ratio on both sides of the link, relating to both the base station and user equipment. So from the figures shown in the table, it can be seen that Cat-M1 and NB-IOT offer improvements over current GSM technologies at a reduced power level. The reduction in power is an important factor, as well as simplified signaling processes and power-saving features to achieve one of the key goals of the technology, long battery life. So as well as achieving low battery consumption, an improved flexibility is afforded in where the device can be located in its operating environment. Areas where traditional cellular technologies have not been suitable for various reasons, including coverage and battery life, an option now exists. And it's important to remember that IoT technology is complementary to other cellular services and not necessarily a replacement, and its use will depend on the end user's application. So it can be seen from the various 3GPP releases that additional bands are being allocated for IoT use across the globe, and it's reasonable to expect that the list will grow with each new release, with the benefits that device deployment on a global scale will be possible. It's also important to note that the bands for Cat-M1 devices and NB-IOT are not the same, so this may be a factor to take into account when choosing an IoT device technology if your device is to be deployed globally. So Cat-M1 modules are essentially stripped-down versions of LTE. Ultimately, your choice of technology will come down to your application. And it's important to note that there's no perfect solution for every application. Each has its own merits, and there will likely be a best fit for your product. So looking at the infographic, if you want fast data rates, aren't overly concerned with long battery life, and cost isn't a major issue, then LTE would be a good choice. In some applications, there may be no choice. If you need fast data rates above a certain threshold, then this might be the only solution. You've got perhaps a halfway house with LTE Cat 1 and LTE Cat 0, if you can have some compromises. And then at the opposite end of the scale, Cat-M1 has the lowest data rates, but the best battery life, the most simplified design, and importantly, lowest cost. So this slide shows some of the differences between NB-IOT and Cat-M1, and some of the notable differences are in the bandwidth between the signals. NB-IOT uses a 200 kHz channel spacing with 180 kHz bandwidth, the same as one resource block element in LTE. Cat-M1 uses a bandwidth of 1.4 MHz, which is 6 resource block elements in LTE. For Cat-M2, the bandwidth has increased to 5 MHz. One of NB-IOT's key strengths is its flexibility to operate as a standalone carrier or work in harmony with LTE carrier by borrowing a single resource block element or using spare guard band space either end of an LTE carrier, whereas Cat-M1 has standalone operation mode within the operating frequency band. The data rates are different with Cat-M1, offering better speeds in both the uplink and downlink directions, and an additional modulation scheme of 16 QAM as well as QPSK. Higher order modulation schemes equate to improved speeds, but at the cost of sensitivity. And there is an argument for improved battery life due to shorter transmission times through modulation coding scheme efficiencies. Another notable difference is in the addition of a new power class in release 14 for NB-IOT, providing a lower transmit power of 14 dBm versus the previous 20 or 23 dBm. In release 15, devices will also support a new power class of 14 dBm as well for Cat-M devices. So the final two key differences are in mobility and voice support. NB-IOT does not have functionality for voice and has limited mobility applications. Its primary focus is a high link budget, infrequent transmissions, and long battery life. Cat-M1 provides further options, but at the expense of link budget and battery life, and which is the best use case will depend on your desired application. So neither Cat-M1 or NB-IOT is better than the other, but both have their merits and their suitability will vary for each application type. There's a lot of information available on the web from various chipset manufacturers to help in deciding which technology might be right for your application. So just before we move on to some of the technology highlights, I want to quickly explain the modes of operation for NB-IOT that you might have noticed on the previous slide. So NB-IOT can be deployed in a standalone, in-band or guard band mode. And standalone mode resembles very closely a GSM deployment. It has a single resource block, which is a 200 kHz channel spacing, as we've already mentioned, as the same as GSM. This means it's a good fit to coexist with network channel rasters already being used, but it's equally at home being used within LTE networks, either as in-band, where a single resource block is scheduled and borrowed from the main LTE carrier. So in the case of a 20 megahertz carrier, this means the LTE signal will be left with 99 resource blocks, whilst the NB-IOT application uses a single resource block. Alternatively, NB-IOT can be deployed within the network, within the guard bands of the LTE signal. This is normally unused spectrum designed to prevent the LTE carrier from encroaching on a neighbor carrier. So due to the very narrow bandwidth of the NB-IOT signal, it can be placed within the guard band region without violating any spectrum rules. From its positioning flexibility, it can be seen how easily NB-IOT integrates into existing LTE networks, and in the case of guard band operation, no LTE spectrum resources are used. So to briefly summarize the main highlights of cellular IoT technology, cellular networks provide global coverage and don't require the use of any additional gateway to the internet on the user equipment side. This in most cases can simplify deployment, but this can be a problem where an area may not have network coverage. In this instance, another form of IoT solution might be more appropriate. Having an improved link budget over traditional cellular technology makes it use suitable in environments where cell coverage is challenging, for example, basements, cupboards, underground sites, etc. It has the benefit of being plug and play with existing networks. On the operator side, it's usually a software update to existing infrastructure, and using the existing networks, security is inherited from the network in terms of data transmitted to and from the device. Battery life is greatly improved due to infrequent transmissions, numerous power-saving features, including deep sleep modes, and switching off of circuitry during operation times to realize useful device battery life of up to 10 years. Due to the reduced complexity of the modules versus a standard 2G, 3G, or 4G module, their price is much lower and down to around a few dollars. In using licensed frequency bands, devices are afforded spectrum which is protected from interference, and operation is managed by the network in normal use, and careful planning is carried out prior to network sites being deployed to ensure there are no channel clash issues. The whole ecosystem has been designed to be forward compatible with 5G networks, so moving forward, devices deployed today will still work within networks of the future. And another important factor is the number of devices that can be serviced within a single cell. There are likely to be a high concentration of devices operating within a cell which all need service. For NB-IOT, it's been determined that more than 50,000 devices could be serviced by a single base station deployment. So some other notable new features for NB-IOT have led to positioning, So many improvements to narrowband IoT and Cat-M technology have been made since their inception. As with all cellular technology, there is a constant evolution and refinement to improve the operation. Most of the added features focus on battery-saving features, first introduced at release 12, and power-saving mode gives the greatest benefit, but other features have been implemented that, whilst quite small in isolation, they provide a marked power usage saving over a required life of 10 years. An example of this is a new power class reducing the transmitted power to 14 dBm. Some other notable new features for NB-IOT have led to positioning information for the device and TDD modes of operation, along with additional frequency band support. And for Cat-M devices, improvements have been made in mobility of up to 240 kilometers an hour now, a new channel bandwidth of 5 meg for increased throughput, and some scheduling enhancements. Another useful feature introduced in release 14 that might appeal to some users and their NB-IOT application is OTDOA, so Observed Time Interval of Arrival. This feature allows the device to determine its position by measuring the difference between 3 or more connected base stations. The measurements are reported to a positioning server which estimates its location. Whilst this might not be as accurate as a GNSS receiver position, it will be adequate for many users, and reports suggest somewhere in the region of 30 to 50 meters accuracy. can be expected that in future 3GPP releases, further features and enhancements will be implemented. So why would you choose an NB-IOT device? Well, if the key requirements for an application are its deployment into a remote or challenger location, a low transmission rate infrequently, a long battery life and mobility isn't really an issue, then NB-IOT could be a good choice. So some typical applications already using IoT are utility meters, sensors, and various other products, including household devices. And for Cat M1, well, where mobility, voice, or low latency applications are sought, but with an improved battery life over traditional cellular devices, Cat M1 devices may be a more suitable choice. So some of the applications currently using Cat M1 solutions are wearables, tracking applications, and alarm systems, amongst others. Either way, Cat M1 or NB-IOT solutions offer a good option for many IoT applications. So this slide gives a quick snapshot of standards that IoT modules will be tested against to comply with European and US standards. In many cases, these standards are accepted by other regions outside of these markets. However, where there are country-specific requirements, your chosen GMA partner will be able to advise. And my colleague Ryan will cover more on relevant standards in the second part of the presentation. So on to really some test challenges and considerations that from our personal experience in the lab. So something to consider is definitely battery life. Testing in the lab will force the device to transmit permanently rather than its typical duty cycle, which might be once a day. So ensure that sufficient number of batteries are provided for the test program. Does the product have easy access to be able to change the batteries? We've seen some samples which have complex gasket arrangements that may impact the spurious emissions results if not correctly fitted or damaged in reassembly. We've seen some products which have required special tools to dismantle the device. Other cases have included batteries which are soldered to boards, which can be problematic if access is difficult. We've seen some cases where a customer has needed to provide 10 test samples to cover the test time required for RF and EMC testing, as the battery was not able to be replaced. For products which have a small coin cell battery, more samples will be required versus a product which has a higher capacity battery. In some cases, we've seen with partly spent batteries, they've caused connectivity issues. So we were able to communicate with the device via a laptop and send it commands, but when it actually came to connecting with the test set from an RF perspective, the device failed to attach to the test set. So that's something to watch out for. Ensure that the module is set up to be used for the frequency bands under test. If this needs to be configured by the lab, then detailed instructions shall be provided. Where the device supports multiple IoT technologies, ensure that these are active in the device, or clear instructions are provided on how the device can be configured come the time of test. A common problem that we've encountered is where a device fails the requirements of the specification due to other wireless technology within the host product. So ensure that when providing equipment for test at a lab, that any wireless technology that is not under test can be disabled. It should also be considered, though, that had to have the ability to activate all wireless technologies for any coexistence radiated spurious emissions tests that may be required for EU or FCC testing. Whenever providing equipment to a lab for testing, it's essential to provide clear, simple instructions to follow. Whilst manufacturers may use the same technology, each chipset has a slightly different implementation to set various modes of operation, coupled with additional layers of software to make the device carry out its intended use. Test lab won't always be an expert on every single device that comes through for testing, so always write instructions as clearly and as simply as possible to ensure testing isn't delayed. It's also essential to consider the normal operation of your product, and this might not be testable in a lab environment. For example, a module that transmits once a day for a few seconds will not be testable. In the case of cellular modules, this is not as important, as the test set can help overcome these issues by forcing the device into a more regular transmit pattern. There could be some cases where additional effort may need to be considered prior to testing to modify the main application or to provide a test application to enable testing to be carried out. An example of this could be a product which needs to access an external server. If this server is not seen, the link will be dropped. There are ways to configure the test set to enable access to the outside world, or alternatively a modification to the application software to remove the dependence on that external server. It's recommended that prior to starting any testing, consultation with your chosen lab is done in advance to save any delays at the time of test. So which countries will your device be used in? It's a good idea to discuss your test strategy with your chosen lab relating to frequency bands. In some cases, the number of bands to be tested can be rationalized. If the device is only for sale in one country and will never roam, you might be over-testing, increasing your test time and costs. And eSIM is something now that we're starting to see some more of. Many devices are too small to utilize a traditional SIM size, even nano. So some manufacturers now are switching to eSIM due to its size advantage and cost. If you are going to be providing samples that have an eSIM, ensure the device you're providing for test has a test profile configured on the eSIM. And you can find out more information about the profile on the eSIM at the from a GSMA document, SGP.22, section 2.4.5.3. And this guidance document can be downloaded free from the GSMA website, where there's a lot of other useful information there as well. If you're going to store multiple profiles on the eSIM, so perhaps you've got a network operator profile and a test profile, this should be selectable by the lab or pre-selected before submitting to the test lab. Due to the unavailability of network operator security parameters, it won't be possible to connect the sample to the test set in the lab, despite connectivity being available with the sample on a live network. And if you're still using a standard test SIM, then we'll need to be able to access the SIM slot to insert one of our test SIM cards. So lastly, despite Cat-M1 supporting a 1.4 MHz bandwidth when all 6 resource blocks are used, there can be problems connecting to the device under test with the test set when using that bandwidth. So I've put a table there from 3GPP TS36.521. This can be referenced to establish which bandwidths are supported for the Cat-M1 device. So whilst the bandwidth may only be 1.4 MHz with 6 resource blocks, it can coexist with 1.4, 3, 5, 10, 15, and 20 MHz bandwidths. And we've seen issues where, for example, on band 1, we've tried to connect using a 1.4 MHz bandwidth. There's been no connectivity, and it took us a little while to figure out why that was. But as soon as we set the bandwidth to 5, 10, 15, or 20, then the device would connect. So the little diagram on the right there is really just to show, whilst we might have a 5 MHz bandwidth, that Cat-M1 could coexist within that 5 MHz band. So cybersecurity is a new requirement. It's now gaining more traction. We're all aware that this is an issue, and until recently, there haven't been really any regulatory requirements. Within the EU, ETSI have now have EN 303645 for consumer IoT devices, such as baby monitors, smart cameras, TVs, health trackers, smart home assistants, door and window sensors, plus many others. Currently, this is not mandatory for compliance with the RED. However, this is likely to happen via a delegated act in the future. In the US, in California and Oregon, cybersecurity is now mandatory, with devices being tested against NIST 8259. And it should be noted that the current standards are a baseline, and there might be some further testing that you want to carry out depending on your application. So just a few last thoughts regarding choosing a lab to carry out your cellular IoT testing before moving on to the second part of this webinar. Does your chosen lab have 17025 accreditation? A lot of countries are now insisting on reports which are accredited, and we've seen several instances in recent times where reports have been rejected due to them being unaccredited. Does the lab cover the relevant countries from a test and certification perspective that will enable you to sell the product in your target markets? Does the lab use test automation? Do they have experienced engineers? What's the report delivery time? And are they able to offer parallel testing for different disciplines, such as RF, EMC, and safety, in cases where you've got tight deadlines? Can the lab help you gain access to all the markets you need to deploy into your finished product? And can they assist with cybersecurity requirements? So for myself, that concludes the first part of this webinar where we gave an overview of Cat M1 and NB-IOT devices and some of the test challenges and considerations. And I'd like to now hand over to my colleague Ryan, who will talk through the certification of modules.
Okay, thank you, Simon. My name is Ryan Henley, and I'll be talking to you a little bit today about module integration and the regulatory requirements for FCC, ISED, and the RED. So, if we start on what is a radio module, so it's a separate circuit board containing all the circuitry to transmit and usually receive RF energy. In many cases, it has an integrated antenna or sometimes a connector to attach an external antenna. It's only missing an input signal and a power source to make it functional, and it's designed to be installed or attached to a host product. A radio module could be transmit or receive only, but most include transmit and receive to provide that wireless functionality. Radio modules are also typically shielded to limit unintentional emissions and increase the EMC immunity performance. This next slide shows some examples of types of wireless communication that RF modules use. So Simon had some examples on his presentation, but there's a few more listed there. For FCC, a certified module is one which has been issued a United States FCC grant of authorization. And for RED, it is one which is compliant with the essential requirements of the Radio Equipment Directive. So for FCC and ISEDC for Canada, these are the types of modular approval. So most RF modules have what's known as single modular approval, which must satisfy all of the 8 grant conditions listed there. Many module integrators will use modules which have FCC and ISEDC single modular approval, but the other types shown there are certainly something to be aware of because there are constraints to be aware of as shown there. What is a host? So a host is a product containing the radio module, and nowadays, with the need to make everything smart, there are many examples of host products integrating wireless modules, and a few examples are listed there, but there's obviously many others nowadays. And the final radio product is the combination of the host and the radio module. A composite device, defined actually in FCC Rule Part 15.31k, as shown there. Many products these days have multiple radio modules inside, so that would be an example of a composite device, and each radio transmitter must show compliance to the applicable standards. The final composite product would have one FCC and ISEDC identification number. This slide shows some very useful knowledge database documents on what you would need to certify a module, and there's also some guidance for host manufacturers integrating a module. Also one there on the labeling requirements, and these are all publicly available from the FCC website. This slide specifies some general guidance for host product manufacturers. Firstly, you should review the modular transmitter test reports, which are publicly available on the FCC website, and that will enable you to do a comparison between the host product testing and the modular testing to see if there's any degradation in the red emissions profile. If during the host product testing you find out that there is some degradation to the point where it exceeds the limits, then it may be necessary to work with the module manufacturer to sort that problem out. Any changes to an approved module and antenna must be reviewed against the FCC and ISEDC permissive change policies, as well as the PAG list. That stands for pre-approval guidance, if that is required. There's a final note there to emphasize that if the final product fails the limits, it's the responsibility of that final product manufacturer not to market the product in the US or industry or Canada. It's not the module manufacturer's responsibility. Your responsibilities as a host manufacturer, you need to ensure compliance covering the digital circuitry or the unintentional radiator part, and also all of the transmitters, including certified ones that are being used in the host product. You should review the integration instructions provided for the certified module and ensure all the items are addressed. You need to maintain the documentation on how the host product with the certified module complies with the FCC and ISEDC rules, and be aware that if the module is certified as a limited modular approval, the integration instructions must be followed to ensure the conditions are clearly addressed. Continuing on, RF exposure is a very key issue that needs to be addressed. The modular integration instructions should either specify a distance of 20 centimeters or more between the antenna and the persons, or alternatively, it can be installed closer than 20 centimeters to the user or a person, but installed in a specific type of host. As well as this, the module may also be certified to be used with other certified modules which could transmit at the same time. And if there are no integration instructions relating to RF exposure, i.e. there's no distance specified, then the device could be exempt from SAR testing, but you would need to check the grant of authorization for each radio transmitter to find that out. A host product manufacturer can contact the module manufacturer if the integration instructions do not contain clear direction for the integration of limited modules or for RF exposure. And if any of these integration issues are not resolved, then a host product manufacturer really has three options. You can ask the module manufacturer to file a Class 2 permissive change to address the issue. The host product manufacturer can file for a change in FCC ID, which is effectively a new application, and then file a Class 2 permissive change. Or finally, the host product manufacturer can file their own modular or entire host product application, and there is a KDB reference there which describes this in a lot more detail. I mentioned the unintentional radiator part at the start of this section. So this compliance host product is in accordance with FCC subpart 15B, and then you need to establish the appropriate authorization route, which can either be the self-declaration route known as SDOC, self-declaration of conformity that stands for, or alternatively the certification route. However, if the applicant is not located in the USA, the certification route must be followed. If the applicant is in the USA, then you do have the option of using the SDOC route or the certification for the 15B portion of the device. If the certification route is used, then there are a couple of examples of equipment authorization classes for a Class A and Class B digital device there. For FCC using the SDOC, the 15B report, the test report is held internally, and the same for Canada, although there is no certification requirement for Canada for that unintentional radiator part. A host manufacturer is responsible for testing and certification for any other transmitters which are not certified as a modular transmitter. And you should also perform the investigative measurements on the host containing the certified transmitter module to confirm that there is no degradation and the host product meets the FCC and ISEDC requirements. And you can do that by operating the host with all the transmitters operating at the same time. That test report is held by the host manufacturer as the evidence of compliance. The host product manufacturer has labeling requirements depending on the authorization route which is used. So SDOC for the 15B part, devices shall be uniquely identified by a label containing the trade name and the type or the model number, and also bear the statement specified in section 15.19A3 in a conspicuous location on the device, or alternatively in the manual if the device is too small. A compliance information statement must be supplied with the product at the time of marketing, containing the identification of the product, the compliance statement, and the name, address, and telephone number, or the internet contact of the responsible party. As I mentioned before, the responsible party for supplier's declaration of conformity must be located within the United States. Finally, if the host contains certified modules, there must be a label for each approved module that shows contains or includes FCC ID, and then the X's and the Y's there should be replaced by the actual number of that certified module. And similarly for Canada, you've got contains or includes IC, and then a reference to that certified module again. And you're also permitted to place that this in the user manual if the product is too small. On to the RED, the Radio Equipment Directive, the European compliance. But unlike FCC or ISEDC, there's no such term really as modular approval, but it is very common these days to buy a radio module or a chip which has been assessed to the essential requirements of the RED. The radio module is typically assessed for its intended use, and therefore very important for the module manufacturer to specify how the module has been assessed and the conditions for compliant use. And the combination of the host and the radio module becomes the final radio product, and needs to be assessed to the essential requirements of the RED if at the time of placing the product on the market, the radio is incorporated into the host product and permanently attached, and cannot be easily removed. Compliance with the RED is against the essential requirements, so a full assessment of safety, EMC, and radio performance is necessary for a radio module to show that. If the intended host is known, the module manufacturer can assess the radio module in the intended host and the environment, but if this is not known, the module manufacturer must define at least one operating environment for the assessment, which must be clearly shown in the technical documentation. That's actually a really important part because it shows an installer the environment in which the radio module is compliant. Any combination of host and radio module effectively becomes a new product, and this new final radio product should be assessed to the essential requirements of the RED. The manufacturer placing the final radio product on the market is responsible for the overall compliance of the final radio product. Some form of assessment will be required on the final radio product which incorporates the radio module if the host wasn't used at the time of the radio module assessment. A few times I have heard that an approved host now integrates an approved module, which means that the new final radio product is approved. That is certainly not the case, hence the comment there indicated that CE plus CE certainly doesn't necessarily mean the final product is compliant. When you assessed against the essential requirements of the RED, a lot of this is very specific to the host environment, so any change can potentially affect the safety, EMC, and radio performance. That is why the final radio product must be assessed to the essential requirements of the RED. However, there is a desire for module integrators to avoid repeating the radio performance assessment of the final radio product if that can be justified. And that's really driven the need for module manufacturers to assess the radio performance, which effectively allows the RF conducted portion of the radio compliance, the radio module compliance, to be used at final radio product level, which is obviously great news for module integrators. If there's no assessment of the radio performance of the module, or this information cannot be obtained by the final radio product manufacturer, then a complete assessment of the radio performance is required. Any information relating to the compliance of the module and the responsibility of the final radio product manufacturer should be made clear in the information provided by the radio module manufacturer in relation to the installation and the intended purpose. Product safety under Article 3.1a always applies to the final radio product. The safety assessment takes into account the application of the product and the environment it will be used in, and a safety assessment on a radio module doesn't provide any confidence of safety compliance on the final radio product. However, RF exposure, also under Article 3.1a of the RED, may be able to be used if the RF output power of the radio module meets the low power exposure compliance level, or the radio module shows exposure compliance at 20 centimeters and at least that same separation distance to the user is the case in the final radio product as well. EMC testing under Article 3.1b of the RED will apply at final radio product level, which in most cases means full EMC testing, because EMC tests on a radio module don't provide confidence of EMC compliance at final radio product level. Article 3.2 of the RED is the radio performance aspect, and a full assessment is required at final radio product level. I briefly touched on this earlier, but this does not necessarily mean full radio testing of the final radio product. Radio tests that have been performed by conducted means such as bandwidth, transmitter timing, duty cycle, frequency hopping rates, etc., which have been performed on the radio module may be considered as the same when the radio module is installed in the host product. And you could apply that justification to all the conducted measurements performed on the radio module, including transmitter and receiver tests at the decision of the manufacturer of the final radio product if the installation is considered to not affect those measurements. The voltage variation tests should have already been assessed by the module manufacturer for standardized connection types, so shouldn't need to be repeated by the final radio product manufacturer. So in terms of what radio performance tests you should repeat on the final radio product, these are typically radiated spurious emissions, effective isotropic radiated power, or effective radiated power, and possibly some critical receiver performance tests that are not comparable to the radio module test results. The reason for repeating these tests is because the installation of a radio module into a host product may cause reflections or shielding of radio signals, and reflections can certainly increase radiated levels of spurious emissions and EIRP or field strength levels, and shielding, on the other hand, can decrease radiated levels, which could affect the input levels to the radio receiver. You may also be using your own customized antenna, which is a key component of the of the transmit and receiver radiated performance of the final radio product, and some assessment under Article 3.2 of the RED is certainly required. To summarize Article 3.2 there for the final radio product, where the radio module test data is available, the final radio product manufacturer may choose to only test the radiated performance test cases, such as radiated spurious emissions, EIRP, and critical receiver performance tests. The final radio product manufacturer could also choose to perform partial testing on those tests as well. So where the radio module has performed tests on multiple modulation modes and bandwidth types and data rates and on 3 operating channels, the final radio product manufacturer may choose to retest only the mode and the channel which produced the worst case test results at the radio module level. Excuse me. The idea is that you reach a point where enough testing has been performed which shows evidence of compliance of the final radio product in conjunction with the compliance at radio module level. This slide is a point to note for any module manufacturer or final product manufacturer. An LTE Cat M1 or NB-IOT module would require the involvement of a notified body, and that is because the applicable harmonized standard under Article 3.2 of the RED covering that technology is ETSI EN 301-908-13 version 13.1.1, and this version is not currently specified in the RED official journal, and that's the official list of harmonized standards. That means that a final radio product cannot be legally placed on the market without following the Annex 3 conformity assessment procedure, and a notified body will review the technical documentation, including all the evidence of compliance, and they will provide a type examination certificate. Just because the radio module has been tested to ETSI EN 301-908-13 version 13.11 does not negate the need to do this, because it is applicable at final radio product level. So those keen of you to do a bit more reading can download a copy of ETSI EG 203367, which is a guide to applying harmonized standards under Article 3.1b and 3.2 of the RED for multi-radio and combined radio and non-radio equipment. And there is a lot more detail in this guide than I have time to speak about today. The first half of the presentation by Simon was obviously very focused on LT, Cat-M1 and NB-IOT. So my presentation concludes with the final slide showing compliance, so showing some FCC and ISCDC standards that are applicable. Similarly, some harmonized standards which are used to demonstrate compliance with the essential requirements of the RED. As I've stated earlier, the 15B and the Canada equivalent is all about covering the unintentional radiator part of the final product. The RF exposure conditions certainly need to be addressed, and the FCC and ISCDC standards are applied depending on the transmitter frequency band of operation. So, that could be part 22, 24, 27, some Canada equivalents listed there, but really depends on the frequency band of operation. The essential requirements of the RED is shown there below the FCC and ISCDC. RF exposure conditions also need to be considered. A safety assessment under Article 3.1a is required, and I have used EN 62368-1 there as an example, which covers audio, video, information and communication technology equipment. A point to note there is that EN 60950-1 will be withdrawn on the 20th of December this year, so an update to EN 62368-1 is required if placing products on the market after that date. ETSI EN 301-489-1 and -52 are specified there for EMC compliance. Now, -1 is the common technical requirements, and -52 is the specific conditions for the cellular communication and user equipment. It would actually be -50 if the final product was a cellular base station. And finally, ETSI EN 301-908-1 and -13 are the two applicable standards under Article 3.2. -1 is the common requirements, and -13 contains all the other tests which would be applicable for an LT, Cat-M1 and NB-IOT module. And there's a note there, to emphasise the point that at the moment a notified body must be involved in placing the final radio product on the market, and that's likely to change in the future, but that is certainly the case today. That concludes my presentation part. So I guess can I hand back to Richard now?
Thank you very much, Ryan. So we have a little bit of time, and we've just got a few questions that we just want to run through that have been submitted. So the first question I've got is, how many devices are using eSIM versus normal SIM?
Yeah, I guess I'll tell Richard. Actually, not many at the moment that we've seen through the lab, but we are expecting. We've seen some samples now that are using it, but we're expecting to see a lot more in the future due to cost considerations, and convenience, and just the physical size. At the moment, nano SIMs with the SIM card holder are just not going to be practical for some types of device, particularly some of these smaller IoT devices. So we're expecting to see a lot more, hence why we kind of covered that on the webinar. So manufacturers are aware of what they may need to set up before they send the devices into the lab.
Okay, thank you very much, Simon. I've got a couple more questions here which I think are aimed at Ryan. So the first one of these is, can UK manufacturer with a US sister company apply SDOC by the company?
Yes, the answer to that is yes. The key point there is that the applicant, which can be the manufacturer, it could be the office in the USA, it could be even a representative of the company in the USA. So if you have any of them, the key point being that the applicant must be situated in the USA. But in answer to your question, is yes.
Okay.
Your US sister company can apply SDOC because they become the applicant.
Okay, thanks, Ryan. And another one here is, does a Cat1 radio need approval by a notified body?
Not Cat 1. It's only sort of pre-release 13 that need the involvement of a notified body. So there is previous versions of 301.908-13 are present in the RED official journal, so that they would cover a Cat 1 device. So you do not legally need to involve a notified body there. You can follow the Annex 2 route, which is effectively the self-declaration. Yes, yeah. Sorry, just make the point there. If it was Cat M1, then that would fall under Release 13, and you would have to involve a notified body in that case.
Okay. Okay, I've not got any more questions at the moment. So with that, this concludes our event for today. On behalf of both your presenters, I'd like to thank you for joining today's event. For more information, please visit our website, www.tuvsud.com/UK. And if you've got any questions, then you can by all means send those through and we can answer those offline. Thank you for attending.